All right, last lecture. So at this point we're going to cover imaging with CCDs and CMOS arrays. And this touches on some of the topics you'll find in both Chapter 8 and 9 in the book. So I've kind of put this together best I can from several sources because the textbook does not have enough information to treat the subject alone. And what we're talking about has applications anywhere from the cameras in smartphones to the most advanced tools used in medical imaging. A little bit of history. This is the oldest photograph ever taken that has been preserved and survived. And this was basically done by exposing a special type of tar to light for at least 8 hours. And you were able to get an image like this. So this is maybe the first type of camera we ever had, and we've seen things change substantially since then. And as we go to the digital age, if you want to look at the first digital camera, it's right here. So you look at 1975, and Steve Sasson of Kodak. This was not exactly a smartphone, but it could record 0.01 megapixels. And it took about 23 seconds per image, recording it onto a tape. So this is where we began. And some of the first consumer products in terms of semiconductors used to record images was the Apple QuickTake, 1994. Was not a success at the time. They were a little bit ahead of their time, I guess. And if you look at what had basically 1 megabyte of memory, and it could take 0.3 megapixel type pictures. So, here we are today in something a bit newer. So let's look at a modern camera or smartphone or microscope imaging device, whatever, and look at this part here. Not all the other electronics, but let's look at the actual chip here for which the light comes in and it detects the image. When we look at the chip, it looks something like this. And if we look closer, we're going to see a bunch of pixels. So let's start to understand how those pixels are built up. So the pixels, there's a couple ways we could do that, and one of the ways we could have the pixels work is using a photodiode, okay? And so I'll talk about that in a second, and that would basically be a reverse bias diode where I get more current as light shines on the diode and I generate electron-hole pairs. So, how would you make a 1 megapixel camera? How would you do it? Well, the obvious approach you're probably thinking about is to use photodiodes. But let's look at the non-obvious approach first, which historically was the first approach because it was actually easier to fabricate than a large array of photodiodes. So the first type of imaging devices that gained commercial success were based on metal oxide semiconductors devices, and they were called charge coupling devices, or CCDs. And so what you had is you basically would shine light on a simple MOS device, metal oxide semiconductor, but you have to have it set up in the right state to receive that light and make some kind of meaningful change. And so for MOS, remember we had accumulation, flat band, depletion, and inversion. Let's ask a couple key questions. So if I shine light on each of these conditions here, each of these conditions, right underneath the oxide, in which case would I see the largest change in photo-generated current, or charge, photo-generated charge? Would it be accumulation? Well, the answer is no, because I already have a ton of holes here, and so if I optically generated, electrons would go this way, holes would accumulate here that are optically generated, but I already have a ton of holes. I'm accumulating them, so I wouldn't see a big change. Same for flat band. This is p-type material, so I still have a ton of holes here, so optically generated charge would not be significant. Look at inversion. Well, in this case, generate electron and holes. The holes would go out here, so I wouldn't collect any holes here, so that wouldn't help me. Electrons would get stuck here, but I'm already generating electrons by inversion, so I wouldn't have a big change in charge here either. So the ideal case would be to use this metal oxide semiconductor device in depletion, because I could generate electron hole pairs. Holes would go this way, but look at the electrons. They would sit here and they would stay. And remember, at this point, there are barely any electrons whatsoever here. This is depleted of holes, and because it's p-type material, there are very few electrons which can diffuse over this way And so photo-generated electrons could absolutely dominate the concentration of electrons I find here right underneath the oxide. So this would be what we call a very simple charge coupling device, which could be made into a high-resolution array easily. All I need is semiconductor wafer, oxide, and a bunch of metal pads wherever I want to basically make a charge coupling device. And the metal could be a transparent metal contact like indium tin oxide, ITO. But the key question is, how are we going to get the charge out? So how we get the charge out is as follows. But let's first basically focus, before I get to that, let's talk about how much charge we can capture. Then I'll talk about how to get the charge out. And so photons of light come in, you generate electron hole pairs, electrons go this way, holes this way, and I start to accumulate electrons here. The number of carriers I'm generating is determined by the optical generation rate, how many photons are coming in per cubic centimeter per unit time. And for a photodiode, I had the following equation, right? And so I had, this was, if I took the width of the region which basically collected photogenerated current, it was diffusion length of the depletion region for holes, diffusion length for electrons on the p side, and the depletion width. How would I change this for this case? Well, it's simple. I still have a depletion width. You can see that by the band bending. So I still have depletion width. I still have Ln, electrons photogenerated within a diffusion length of the depletion region will be created. They'll move around and they will diffuse over this way. So that still happens. But what I don't have is Lp. That disappears because I'm missing the normal p side. If this was a diode, I'd have the bands go like this. I'd have holes generated over here which could also contribute. But in this case, the p side is missing. So I remove that, and this is my new equation I can use to calculate how many carriers I could generate under this oxide. So I know I don't have current flowing though, so I'm just building up a Q. So how much Q can I generate? How do I calculate that? Well, the total charge you would create would be the optically generated current times the frame rate. So how long are you collecting it? So if one frame of a camera records for a certain period of seconds, and this is how much current is being generated during that time, the total charge will be the coulombs per second times second, just giving me coulombs. And that would be everything I had up here, IOP, right, what we had here, times the frame duration. And the frame duration, the inverse of that is the frame rate. So if I have a camera and it's recording video at 30 frames per second, that would be 30 hertz. And my duration for each frame would be easy to calculate. That would just be 1 over 30 in terms of 1 over 30 frames per second in terms of seconds. So that would be, 0.03 seconds would be my duration I would put in here for how much Q I could generate while the camera is capturing one frame of photo-generated charge. So that already tells you right now, right off the bat, why high-speed cameras are more difficult and more expensive. You don't have as much time to generate the charge you need to collect to get a strong electrical signal. So when you go to high-speed cameras, they have to have much more sophisticated electronics and amplification to basically capture the amount of charge you can see electrically within a very short frame time and a very high frame rate. So let's figure out how we can start to move this thing now, and I'll use some figures from the book at this point. So if I look at this pixel here, this is a single pixel. How I'm going to make this is I'll have a metal here, okay, and it could be a transparent metal such as ITO. Here's my oxide. Here's my substrate, and I've created this well here by putting a positive voltage on this side, which brings the bands down and creates a potential well for electrons. That's what I'm showing here. This is the depletion region where I put a positive voltage here on the metal. It bends the bands down here, and in addition to depleting out the holes, hence why it says depletion, it can collect electrons. If I looked at this as a cross-section in this direction, like this, and I plotted potential versus distance, the potential would look like this. Then it drops down, and then it goes back up. So this is basically modeling somewhat like what the conduction band would look like across here. You move this way, then all of a sudden you experience this positive potential which pulls the bands down, the conduction band drops, and then you get to the other side and it comes back up and reaches the normal level here. And so again, you're creating a well for electrons, and this is the electrons here which are stored. You store them in this well under the metal by putting a voltage there. So how could we move this? Well, if we basically start to put more electrodes out here, we could potentially start to shift the well left and right and basically move this bucket back and forth to get the charge out of the device. So here's how you basically take a charge coupled device array, CCD array, and you read the charge out. And so I will collect my charge under these gate electrodes here. I'll put a positive voltage on them to create these buckets to collect photo-generated charge. And then I want to start to read this out to the edge of my device, where I can attach it to electronics and detect the amount of charge generated. So then I'll put a positive voltage on these electrodes as well. That creates a potential well next to this one. The electrons spill over into the entire bucket. Then I'll take the voltage off these gate electrodes here, using this line here. That basically raises the band, the conduction band up. The electrons spill over into that bucket, and then I'll leave it at a state where only this line and these gate electrodes, G2, are on, and the bucket has moved over one position from here to here. If I want to move on to the next, G3, I do the exact same process, and I can use this to move the charge from position to position to position on out to the edge of this array, where then I can read it out with the electronics. Again, the readout charge is proportional to the number of photons absorbed times the length of the frame before I read out the charge, like I said before. And so you only have so much time to absorb these before you have to move them to absorb photons and generate charge before you have to move it out and then reset this to go on to the next frame. So that limits essentially how quickly you can record with this type of device, and furthermore how sensitive it can be in low light conditions. So here's a nice way to visualize this in 2D format, because all CCDs, typically, you see in a camera of course, are 2D. So there's a simple bucket brigade analogy here, where here's all my buckets to collect electrons. These will be potential wells in the conduction band. And my raindrops will be photons coming in. And then what I do is I start to shift those out one row of one column, shift them out one column at a time, dump that into my readout electronics, which then reads that out serially and stores the information. So I basically read out one column, I shift the columns over, read out one column, and then I look at each data point in that column and start to record the image one pixel at a time. Here's an example CMOS sensor. This is a CCD sensor, 1036 by 1010. You can see this one goes up to 30 frames per second. And most importantly, this has a huge dynamic range, 60 dB in terms of the difference between the lowest intensity of light and the maximum intensity it can detect. You'll see this is one of the advantages that CCDs have traditionally had, is the ability to do very high dynamic ranges. Furthermore, the pixels are very small, only 8 microns. Why can they be so small? Well, it's simple, because all I have to do is basically take a metal oxide semiconductor device and just pattern an electrode on the top, and I've created a pixel. So very easy to make these small. Now if you have a CCD or CMOS array, and we'll talk about CMOS arrays in a second, you can run into pixel blooming. So what causes it? So if I have bright spots, and they can cause streaks in the camera, or they can wash out the image completely. Well, pixel blooming is when you have too much light coming in, such to the point where your electrons start to overflow your bucket and start to spread out across into other pixels as well. So much light comes in that the electrons overwhelm the carrying capacity of this potential well bucket. So how do you fix this? Well, what they typically do is, here is your potential well, your photodiode, or this is the MOS structure here, that detects the electrons and puts them in this bucket here. So here's my electrons. This is kind of like my conduction band edge. When I want to read the charge out, I have a transfer gate here, which will then take the electrons, and then I'll push this band down, and the electrons will go over here to my CCD phase gate, which I can use to read it out. But importantly, they put over here an overflow gate that if I have too many electrons, instead of starting to spill over to adjacent pixels, they will go over to this overflow drain here, which can basically absorb excess electrons if needed. So there are things people do to basically create a reserve bucket to deal with too much light hitting a particular pixel so it doesn't spread to adjacent pixels as well. Here's a modern CCD array, and you can see here's the pixel cell here, along with several other features as well. And there are also a couple of the other features we talked about, the photo array that actually collects the charge, transfer gate, and things like that as well. So at this point, here's some review. Take a break. You should be able to calculate this. You should be able to answer what happens if we change our frame rate. This is pretty easy to answer, and as should be this as well.